is introduced what's called the paired t-test. This is an improvement of design. The objectives in a lot of statistics is to find differences if they're there, and to make sure that differences are picked up. So the paired t-test. Quite often we're interested in comparing two treatments, and these two treatments result in two different populations. We might be comparing two diets on weight loss, two drugs that are designed to reduce cholesterol, and we want to compare the drop in cholesterol from the effect of the two drugs. The effect of two methods of teaching mathematics. One method might be better than the other method. One possible design is to randomly divide subjects into two groups. The first group will receive treatment 1, the second will receive treatment 2. So we'll collect data on the measurement. The X values are the measurements on whatever we're measuring for treatment 1. The Y's are the measurements for treatment 2. This design is called the independent sample design. The observations in one sample are not related to the observations in the other sample. Here we use what's called the two-sample t-test. There's the test statistic. It's x bar minus y bar, s pooled, square root 1 over n plus 1 over m. And we rejected from underneath the t distribution, the degrees of freedom is n plus m minus 2. The matched pair design. This is an improvement in the design. So prior to assigning the treatments to the subjects are paired into groups of similar pairs. That way, the difference between the two treatments will be more reflective of the actual difference in the two treatments. Suppose you have n pairs of subjects. So we have a total of 2n subjects. Then you assign the treatments to each pair, one treatment to one member, the other treatment to the other member. So the data collected will occur in pairs, x1 and y1. X will be the measurement, the response for the member of the first pair that receives treatment 1. Y1 will be the measurement of the second pair that receives treatment 2. And this is the same for 2 and 3 and up to n. So xi is the measurement of the response for the subject in pair I that receives treatment 1. Yi is the measurement of the response for the subject in pair I that receives treatment 2. So the observations in the two samples, the two treatments, are matched together. Let di be the difference. This will be a sample from a normal distribution. The mean will be equal to mu2 minus mu1, and mathematically you can find that the standard deviation of the differences is square root sum of the two standard deviations squared minus twice the correlation between x and y times the standard deviation of x times the standard deviation of y. Now, the higher the correlation, the smaller sigma d will be, because that thing that we subtract will be larger in value. So this will occur. The high correlation between x and y will occur if we've matched the subjects up effectively. To test whether mu1 equals mu2 is equivalent to testing whether mu-d is equal to 0. The differences is equal to 0. So the test statistic is the single sample t-test based on the differences. Take the averages of the differences, compare that with 0, which would be true if the two treatments were the same, standard deviation of the differences over the square root of n. Example, suppose we're comparing the effectiveness of two methods of reducing cholesterol. One is to use a specific drug. The other method is to control the diet. We have a total of 8 subjects. They're grouped into 4 matched pairs. Probably you'd match them according to their initial cholesterol level. In each matched pair, one subject was given the drug treatment, the other one was given the diet control treatment. The assignment of the treatments in each matched pair is done at random. There's the data collected after a 6-month period. This is the reduction in cholesterol. These are the ones who had the drug treatment. These are the ones who had the diet control treatment. Looks like the reduction for the drug treatment is always seems to be a bit higher, except in this case here. So we compute the differences. So basically we're wanting to know if the differences come from distribution that has a mean of 0. So we just use a one sample t-test using the differences. The average difference, 2.3 divided by standard deviation of the differences divided by the square root of n. N was 4 here, is 1.23. You look at a critical value, 0.025 for 3 degrees of freedom, it's 3.182. The test statistic is well within the acceptance region, so we accept H0. Another example. In this example, we're interested in if an antidepressant drug is effective in reducing depression. So the subjects were given a test measuring depression. At the beginning of the study, they were given the drug, and then after the period of 1 month on the antidepressant, they were given the test again. So there's 2 scores, the pre-score and the post-score. Did the drug have any effect on reducing depression? There is the data. So this is the pre-score measurement. This is the post-score measurement. So this is a typical, quite often matched pair experiment. The matched pair is the same subject. Person is his own matched pair. So this is before, and this is after treatment with the drug. We want to know whether the differences here are on the average 0 or whether they're positive. So we compute from the differences the mean, standard deviation, and just perform the one sample t-test where I test whether the differences are significantly different from 0. This is great. You want to prove that the differences are positive. You'd use a one-tail test. The critical value, 4.05 with 11 degrees of freedom, is 1.796. The value of the statistic is higher than that, 3.0. So H0 is rejected, and you conclude that the drug does have a significant effect on reducing the score on a depression test. So the last example is a match pair experiment that occurs quite often. You have two observations on the same subject, so each subject is its own match pair. One observation was the pre-score. The other observation is the post-score after the treatment. So the subject is his own matched twin. This sometimes is called a repeated measures design. When you have several measurements on the same subject, that's called a repeated measures design. Here you have two measurements, the pre-score and the post-score. Another example, here we're interested in determining if a new method of mathematics instruction is an improvement over the current method. So to carry out this study, 20 grade 4 students were selected. They were divided into 10 matched pairs, so the subjects would be matched according to probably their math ability. One member of the match pair gets the new method, the other gets the current method. Then they're tested at the end of the instruction period. So there's their scores. These are the ones on the new, using the new method. This is using the current method. We want to know whether or not these ones are higher with the new method than on the current method. We look at the differences. Some of them are, most of them are positive, but there's a few that are negative. The average is 4.60 of the difference, the standard deviation. So we do a one sample t-test to test whether or not the differences are significantly greater than 0. Again, the critical value, 0.05, is 1.83. If I was using 0.01, this is a more difficult test. It's 2.831. So the test statistic would have been rejected using a 5% level, but accepted using a 1% level. So just a quick summary of the tests we've learned so far. There's one sample test. These are where you have a single population and you're testing the parameter of that single population. One is where you're testing the mean of a normal population. The standard deviation is either known or you have a large enough sample that you can replace it accurately with this sample standard deviation. There is the null hypothesis that's being tested, and there could be all of these alternative hypotheses. The first case, when it's two-sided, you use a two-tail test. One-sided, you use a one-tail test. Now, if sigma naught is not known but estimated by S, sample standard deviation, then the Z test turns into the T test. The critical region is underneath the T distribution. The degrees of freedom is n-1. Here's the test for testing the proportion. The Z test. We're testing whether the proportion is equal to P naught. This is the standard deviation of P hat if P naught is the correct proportion. There's the critical region depending on whether the alternative is one-sided or two-sided. The tests for a variance. That's, you use this statistic, which has a chi-squared distribution. n-1 times S squared over sigma naught squared. So we look up the critical region underneath the chi-squared distribution. The chi-squared distribution is not symmetric about its center, so the lower limit is attain differently from the upper limit. Here, because the distribution, the normal distribution and the t-distribution are symmetric about 0, the lower limit is just the negative of the upper limit. Here you have to look up the lower limit and the upper limits specifically. Here are the two sample tests where you have two populations and you're comparing the parameters of the two populations. The first two are for comparing the means. This is when the variances are known, or the sample sizes are large enough that you can estimate them accurately with the sample variances. This is the t-test when the variances are unknown, but we also make the assumption that they're equal. Then you have to use what's called the pooled estimate of variance. This then has a t-distribution. The degrees of freedom is n plus m minus 2. Here's the tests for testing whether two proportions are equal. P1 hat and P2 hat are the proportions for sample 1 and sample 2. P hat is the proportion when you combine the two samples, and that's an estimate of the proportion if you did assume P1 was equal to P2. Critical region comes from underneath the standard normal distribution. Two sample tests continued. This is the t-test. This is when you have unknown means, unknown variances. The variances we don't assume are equal. Then you, computing the standard deviation of x1 bar minus x2 bar, you use the sample variance in this. And it's been shown that this has approximately a t-distribution with this number of degrees of freedom. So the distribution of the t degrees of freedom is calculated from this complicated formula. This is the test for testing whether two variances are the same. You use either S1 squared over S2 squared. So rather than using a difference between the two variances to compare them, you use a ratio. It turns out that this is the best way. I could also use it the other way around. What happens is when I use S2 squared over S1 squared, the degrees of freedom in the numerator and denominator switch around. The paired test. Here you have independent samples. That's the independent t-test. The paired test, you have the subjects matched up according to into matched pairs. One subject receives treatment 1, the other one receives treatment 2. We then do basically a one sample test to see if the differences between treatment 1 and treatment 2 are 0 or possibly positive. In the independent samples test, you could have equal numbers on both treatments, or you could have unequal numbers. The observations in the independent sample test are not related to corresponding observations in the other sample. Sample size determination when you're comparing two or more populations. Estimating a difference in two proportions. The confidence limit for difference in two proportions is the difference in the two sample proportions plus or minus an error bound B. The error bound B is Z sub alpha over 2 square root P1 minus P1 over N1 plus P2 1 minus P2 over N2. Usually P1 and P2 are estimated from the data. So when you have two populations, you can make the error bound smaller, small as you want, by increasing N1 or increasing N2 or increasing a combination of both. So there are many solutions that will give an error bound of B level of confidence of alpha. You can make B small by increasing N1 or N2 or a combination of both. So here's some practical solutions to this, so that there's just one solution. One is require the sample size to be equal. This would be the appropriate choice if one researcher was collecting the data from population 1, another from population 2, and you wanted to equalize their workload. Another solution is to choose N1 and N2 so that the required error bound is achieved and the total sample size is minimized. This would be appropriate if you had a single researcher collecting data from both populations and you wanted to minimize his workload. Final one, minimize the total cost of the sample. Quite often, cost of taking an observation from population 1 is different than the cost of taking an observation from population 2. So the total cost of the survey, there's a fixed cost of setting up the survey, and then there's a cost per observation of taking data from population 1, and a different cost maybe from population 2. This is definitely true when you're testing drugs. A new drug versus a placebo. Placebos are really cheap, but new drugs are really expensive. The total cost of the study would be C naught, the fixed cost of just setting up the experiment, times the cost of choosing N1 subjects from population 1, plus the cost of choosing N2 subjects from population 2. So this tries to choose N1 and N2 so that the required error bound is achieved and the total cost is minimized. I'll give you the answers to these in the different cases. You want to estimate with an error bound of B, level confidence 1 minus alpha. In the case when you want both sample sizes to be equal, this is the sample size that will give an error bound of B, level of confidence 1 minus alpha. This is the solution when you want to choose N1 and N2 to minimize the total sample size. This problem is solved using calculus. There's the formulas that give you the sample size required to get an error bound of B, level of confidence 1 minus alpha. It also depends on the total sample size is minimized. Turns out that if the proportion here is closer to 0 or closer to 1, you'll get a more accurate estimate. So this one puts the sample size larger when P1 or P2 is closer to 0.5. This is the solution when you want to choose the sample size, estimate with an error count, the B, level of confidence 1 minus alpha, and you want to minimize the cost. Notice that if C2 was quite a bit greater than C1, you'd choose more observations from population 1 because they're less costly than from population 2. Example, suppose I'm interested in comparing two drugs for their effectiveness. We give the drug for 1 month to 100 patients. Where the two drugs are designed to reduce blood pressure in high blood pressure patients. So we give drug A for 1 month to 100 patients. And out of those, 55 were able to reduce their blood pressure. We give the second drug to 100 patients. 61 patients were able to reduce their blood pressure. So there's the data so far. There's confidence limits for the difference between P1 and P2. The PB hat is 0.61, PA hat is 0.55. We put in the values, that's about over 2. We get 0.06 plus or minus 0.1366. So the error bound is 0.1366, it's 13.6%. Maybe we want something that has a much accurate estimate, much smaller error bound. So suppose I want to determine the sample sizes that would estimate with a smaller error bound 2% rather than 13% with a 95% confidence interval. What should the sample sizes be? The original sample sizes were 100. So this is the formula for N1, NA, and NB if I require the two sample sizes to be equal. These two sample sizes should be 4,662 to estimate P hat with the difference with an error bound of 2%. This is the solution if I wanted the total sample size minimized. There's the formulas for NA and NB. We have estimates of in PA and PB from that original 100. This is 4615, 4707. If you add up these two sample sizes, they'll be smaller than those two sample sizes required to be equal. Suppose that it's much more costly to choose observations from population A than from B. Suppose CA over CB is 10%. Then the sample sizes that would minimize the total cost of the experiment. This is the formula for the sample sizes. Put those numbers in. We get 3,114 from A, 9,654 from B. Guys, it's much more costly to take observations from A than B. Its sample sizes is much smaller. The same can be done for comparing means of two normal populations. There's the error bound. Notice that the error bound will depend on N1 and N2. It also depends on the variability of the two populations. Again, we can choose N1 and N2 subject to certain conditions. This is the formula that will give you your N1 and N2 that will estimate with an error bound of B level of confidence 1 minus alpha. This is if you require equal sample sizes. This is if you want the total sample size to be minimized. This is the sample sizes that would be required if you wanted the cost of the experiment to be minimized. If a population is more variable, sigma squared is larger. More observations should come from that population than from the other one with the smaller variance. If it's less costly to take observations in a population, more observations should be assigned to the sample from that population. You can see that in the formulas for N1 and N2. If C2 is much greater than C1, that will make N1 larger than this quantity here. If sigma 1 squared is greater than sigma 2 squared, more observations, N1 will be larger than N2. Maybe we'll stop at this point. And next time we'll go into the problem of comparing not just two populations, but comparing K populations, more than two populations. So at this point, we'll just end the lecture. And if anybody has any questions, you can ask them now.
Hi, Professor.
Hi.
I was just wondering if the final is going to be a take-home exam like the rest of the tests have been.
It'll be exactly the same. It'll be given out prior to the date, okay?
Okay.
And then you have to submit the answers by a certain time, probably within the next day or so.
Okay, thank you very much.
And the number of questions will be about 3 times the number of questions that are on the individual tests. There's about 20 questions on each individual test on the test. The final exam will have about 60 questions.
Okay, thank you.
Okay. So at this point, I'll end the meeting.